Hi guys, Dr. Musk back again. So we're picking up at section 18.5 where we're going to look at some important amines in the world of biochemistry. So the first class of compounds that we're going to talk about that have amine functional groups in them are plant-based things called alkaloids. So here are a couple of them that you guys have probably heard of before. Morphine and codeine, both very strong narcotic pain relievers. You can see the amine functional groups in both of them over on the right-hand side. And if you classify those, you should be able to tell that they are both tertiary amines. Heroin also is a tertiary amine made from morphine. And because it's less polar than morphine, it stays around in the body longer because it's more fat soluble. So take a look at the difference between morphine and heroin. Not a huge difference. All that we've done is turn a couple of alcohol functional groups into ester functional groups, and that is what turns heroin less polar than morphine and makes it stick around in fat for longer. So morphine clears the body pretty quickly because of those hydroxyl groups. If you've ever had to take morphine in the hospital for really bad pain, you know that they normally administer it through an IV so that they control how much is going in because your body actually clears it pretty quickly. So here is another amine, quinine, and quinine is used as an anti-malarial compound. It also is in tonic water. So if you ever shine a black light on tonic water, it will actually fluoresce. And the fluorescence of tonic water is due to the presence of that quinine, specifically the aromatic ring in there. So that aromatic ring is what causes quinine to be fluorescent. It's really neat if you ever want to take a bottle of tonic water, move it into the dark, and then shine a black light on it. It's pretty incredible. But you can see that tertiary amine in the alkaloid quinine right there. Atropine, another tertiary amine that shows up in deadly nightshade. So this could make somebody have heart failure very easily with even a moderate dose. I think this is hilarious, but during the Renaissance, women used to use this to enlarge their pupils just a little bit by putting a drip of nightshade juice onto their eyeballs. So let's move on from starting to discuss places that we see amines in the world of natural products and talk a little bit more about the chemistry of amines. So we've already talked about the fact that primary and secondary amines can hydrogen bond, tertiary amines can't. But the most important thing about all amines is that they are bases, specifically according to the Bronsted definition. So Bronsted bases are things that pick up H plus ions. All right, they are proton acceptors. So if we treat a Bronsted base like an amine with some sort of acid, something that can give away a proton, then that amine is going to pick up an extra proton. So here we can see the reaction between ammonia, all right, which has that same kind of nitrogen that primary and secondary amines do, and water. And in that case, what happens is ammonia is using its pair of electrons to form a new bond to the hydrogen of water. Because hydrogen can only have one bond, the pair of electrons it is sharing with oxygen moves over onto oxygen, and we're left with a a nitrogen that has 4 bonds around it, which means that the nitrogen atom itself has a positive 1 charge. All right. You're also left with what's left over after water loses an H+, which is the hydroxide ion. So generally speaking, amines don't do this kind of reaction very well with just water. All right. They're not strong enough bases to steal a proton away from water. But if we treat an amine with a stronger acid, like HCl, stronger acids want to give away their H+ ions a lot more than water does, which means that amines can readily take an H+ from a strong acid, like HCl. So what we call amines after they have picked up that extra proton is we call them ammonium ions. So we use that as a general term for amines that have an extra proton hanging out on them and a positive charge. The same way that we refer to carboxylic acids that have lost their proton as carboxylate ions, we refer to amines that have picked up an extra proton as ammonium ions. So note that in this case, because HCl has given away an H+, what's left over after HCl loses that H+ is Cl-. Now, very, very similarly to how losing a proton makes that carboxylate ion water soluble, ammonium ions, because they have a positive charge, are also much more soluble in water than amines are. So this is our way to take amines, even larger amines that would be very insoluble in water, and make them water soluble. By turning them into an ammonium ion, they now have a positive charge and can be readily dissolved in aqueous solution. So that's a really important part of amine chemistry for us to remember. And here are another slide to show you the words that I just said. So by treating an amine with a strong acid like HCl or H2SO4 or HNO3 or HBr or HI, short list of a few very, very common strong acids. Any one of those strong acids, what it's going to do is it's going to give an H+ away to that amine and turn it into a positively charged ammonium ion. And ammonium ions, because they're charged, are very, very water soluble. So let's take a look at a couple of places that ammonium salts are used. All right. So here is an example of Sudafed. So Sudafed isn't very soluble in aqueous solution, except when we give it an extra proton on that nitrogen and make it a charged ammonium compound. All right. So as a charged ammonium compound, it's much more soluble in water and can be transported into the bloodstream more readily. Here's another example of a charged ammonium compound. So Benadryl, the form that it's normally sold in, is as a hydrochloride salt. In other words, we treat the amine version of Benadryl with HCl and give it an extra proton, and that's what allows that Benadryl to dissolve in aqueous solution and distribute in the bloodstream very quickly. Another place that we see ammonium salts is quaternary ammonium salts. So quaternary ammonium salts are ammonium salts where all four of the bonds from nitrogen are to alkyl groups. And what's noteworthy about that is almost all small quaternary ammonium salts like this are very, very potent antibiotics, or disinfectants rather. So antibiotics have to have a specific mode of action. These things are just bactericidal. They kill bacteria like crazy, all right? So because of that, they're added to things like mouthwash, all right? They also don't have a great flavor, which is why most mouthwashes don't taste all that great, because we don't want to swallow those quaternary ammonium compounds. We just want to use them to lessen the bacterial load and then spit them out. So these quaternary ammonium salts have very, very potent activities against bacteria, which is kind of awesome. Thank you guys for paying attention.